Hi everyone, myself Valli Rani, Assistant Professor in Physics in Ramchandra College of Engineering. In this video, we will learn about Fraunhofer diffraction at circular aperture. Before going to discuss about this topic, let me the objectives and outcomes of this topic. The objective of this topic is learning about resolving power of optical instruments. Now let us see outcome. On successful completion of this diffraction video, the student should able to understand the resolving power of different optical instruments. So this is the outcome of this topic. Now let us see the Fraunhofer diffraction at circular aperture. The Fraunhofer diffraction at circular aperture having importance in the discussion of optical instruments such as telescope and microscope. In telescope and microscope, the circular form of lenses are used as objectives and eyepieces. So, compulsory we are discussing about diffraction at circular aperture. For this, consider a circular lens of diameter AB placed perpendicular to plane of the paper. For this, consider a lens of circular aperture AB of diameter D which is placed perpendicular to the plane of the paper. Now, a parallel beam of monochromatic light of wavelength which is allowed to pass through the aperture, and the diffracted beam is focused on the screen by this convex lens. Here, along the diameter of the aperture, the diffraction is similar to the single slit, and every point of wavefront in the plane of circular aperture which is acts as a source of secondary wavelets. So all these emitted secondary wavelets spread in all directions like this. Hence, the diffracted wavefronts along the line of the circular aperture are superimposed with each other and spread at O on the screen. That is, the wavelets traveling along the normal to the circular aperture, and they are travel equal distances, so that the waves are traveling with a zero path difference. These waves are focused at O on the screen, and it is corresponds to the position of central maxima in the form of circular disc like this, called iris disc. Now, the secondary wavelets which are traveling in a direction inclined at an angle theta with normal to the circular aperture, and they are meet at a point O dash on the screen. Here, the diffraction pattern around the iris disc consists of alternate bright and dark rings known as iris rings. So, here the resulting diffraction pattern on the screen is in the form of circular shape like this. The central disc is called iris disc, which is known as central maxima or principal maxima, surrounded by alternate bright and dark fringes rings which are known as iris rings. Here, the point O dash will be maximum or minimum intensity. Here, the intensity distribution at O dash will depends upon the path difference between the waves diffracted at extreme points of the circular aperture. Here, the path difference between the waves at extreme points of the circular aperture is same as the path difference in the single slit of width D. Here, the path difference between the waves diffracted at extreme points of the circular aperture is same as the path difference between the single slit path difference in single slit of width D. To find the path difference, we can draw a normal, a perpendicular from A to B to A called C. This perpendicular line which gives us immediately the path difference between these two diffracted light rays. Here the path difference is AC. To find the path difference AC, we can apply the sine function to this particular triangle ABC. Here sine theta is equal to AC by AB. Here sine theta is equal to AC by AB. Here we find out the AC. For this, AC is equal to AB sine theta. Here AB is the diameter of the lens, which is equal to D. So AC is equal to AB sine theta is equal to AB is equal to diameter of the lens. Then AC is equal to D sine theta. Now we will see the path difference between these two diffracted light rays is D sine theta. So this d sine theta gives the path difference between the waves, secondary wavelets diffracted at extreme points of the circular aperture. So this is the path difference between the waves diffracted at extreme points of the circular aperture. Now let us see Airy disk and Airy rings. Already we have to discuss about what is Airy disk and what is Airy rings in the previous slide. Now let us see Airy disk. In diffraction pattern, the non-diffracted light rays which are traveling in the direction theta is equal to 0, that represents the waves which are traveling with a zero path difference or creates a central maxima in the form of circular disk is known as Airy disk. And we will see Airy rings. Around the Airy disk, the diffracted secondary wavelets or produced alternate bright and dark rings are known as Airy rings. So these are focused at O dash, the corresponding to the position of central maxima. The secondary wavelets which are traveling in a direction inclined at an angle theta, which are focused at the screen, they are formed circular rings called Airy rings. They meet at a point on the screen. At that point we will get alternate bright and dark rings. Those are called Airy rings. That means all the secondary wavelets traveling in a direction inclined at an angle theta with the normal to the aperture and meet at a point on the screen. At that point we will observe the alternate bright and dark rings which are called Airy rings. So this diffraction pattern around the Airy disk consists of alternate bright and dark rings which are known as Airy rings. Now we will see the conditions for bright and dark rings. Here the condition for bright Airy ring. So condition for bright Airy ring is the path difference is 2m plus 1 into lambda by 2, where the range of m is 1, 2, 3 and so on. Here m is equal to 1, which gives the first bright ring. So m is equal to 1, we will get 3 lambda by 2. So this 3 lambda by 2 is the path difference between the waves diffracted at extreme points of the circular aperture. That is, the path difference between the two diffracted light rays is 3 lambda by 2. Then we will get first bright ring in the diffraction pattern which is formed by circular aperture. Here m is equal to 2. M is equal to 2 gives the second bright ring. So second bright ring m is equal to 2, we will get the path difference 5 lambda by 2. So path difference 5 lambda by 2, then we will get second bright ring on the diffraction pattern which is formed by circular aperture. And m is equal to 3 gives the third bright ring. So finally we'll observe the path difference between the waves diffracted at extreme points of the circular aperture is odd multiples of half wavelength. We will get bright ring. This is the condition for bright Airy ring. Now let us see condition for dark Airy ring. If the path difference between the two diffracted light rays is integer multiple of wavelength, we will get dark rings. If the path difference is integer multiple of wavelength, we will get dark rings. Here m is equal to 1, the range of m is 1, 2, 3 and so on. M is equal to 1, it gives the lambda. That is, the lambda is the path difference between the waves diffracted at extreme points of the circular aperture. Then we will get first dark ring. And m is equal to 2. Then it will represent path difference between the diffracted light rays is 2 lambda. Then we will get second dark ring. And m is equal to 3. We will get path difference 3 lambda. Then at that point we will get third dark ring. So this is the condition for dark Iry ring. Now we will see the angular radius of Iry disk. The angular radius means the angular separation between center of Iry disk and first dark ring. Center of Iry disk to first dark ring, dark Iry ring is known as angular radius of Iry disk. That is, the radius of the central disk is the radius of Iry disk. So, we will find out the Iry disk is center of the Iry disk to first dark ring. For this, we find out the radius of the Iry disk. We can use the minimum condition. Here, m is equal to 1, which gives the first dark ring. So, m is equal to 1. Then, d sine theta is equal to lambda. Here, sine theta is equal to, this parameter shifted to this side, we will get sine theta is equal to lambda by d. So, sine theta is equal to lambda by d. Here theta is small, then sine theta nearly theta. So, theta is equal to lambda by d. So, this theta gives the angular separation between the center of Iry disk to first minima. This is also known as limit of resolution. This gives the limit of resolution or the angular separation between the center of Iry disk to first dark ring. So, theta is equal to lambda by d. But this limit of resolution is valid only for rectangular apertures, that is parallel slits only. So, in case of circular aperture, this value will be corrected by George Iry. Like this, theta is equal to 1.22 lambda by d. So, in case of circular aperture, the angular separation between the center of Iry disk to first dark ring theta is equal to 1.22 lambda by d. In case of rectangular apertures, theta is equal to lambda by d. So, this is the angular separation between the center of Iry disk to first dark ring, which is known as angular radius of Iry disk theta, which is also known as limit of resolution. Now, we will find out the radius of Iry disk. The radius of Iry disk, which is the radius of Iry disk, center of Iry disk to first dark ring, which gives the radius of Iry disk. Here, this distance is the radius of Iry disk x, and here the converging lens is nearer to the aperture. Then the distance between the converging lens and the screen, the distance between the aperture and the screen is equal to focal length. Here the converging lens is nearer to the aperture, then the distance between aperture and the screen is called focal length, which is denoted by f. Okay. Now here we will see for this triangle we can apply sine function to this particular triangle. Sine theta is equal to this distance x by this distance f. So, sine theta is equal to x by f. Here theta is small, then sine theta nearly theta. So, theta is equal to x by f. Here the limit of resolution, angular separation between the center of Iry disk to first minima is x is equal to theta is equal to x by f. Already we find out the limit of resolution for circular aperture is theta is equal to 1.22 lambda by d. Okay. Now comparing these two expressions, we will get x by f is equal to 1.22 lambda by d. Here we find out the radius of iridescence. For this f will be, this parameter will be shifted to this side. We will get x is equal to 1.22 lambda f by d. So this x value gives the radius of iridescence. To find the radius of iridescence, first we know the wavelength of instant light, wavelength of instant monochromatic light, and the distance between the aperture to screen and diameter of the circular aperture which is used. To know these values, we can easily find out the radius of iridescence. So this is about radius of iridescence, which gives the angular separation between the center of iridescence to first minima, which is known as limit of resolution. And this Fraunhofer diffraction at circular aperture has a fundamental importance in discussing the resolving power of telescope and microscope, etc. So this is complete detailed explanation about a Fraunhofer diffraction at circular aperture. Now we will see some of the questions about on this topic. Explain in nature of fringes are obtained at a circular aperture Fraunhofer diffraction. Explain the natures of fringes are obtained at a circular aperture Fraunhofer diffraction. Or derive expression for a radius of the iridescence by using circular aperture. So these are the important questions for this topic. So this is about Fraunhofer diffraction at circular aperture. Thank you.